In this lesson, we are going to study injective functions. Let us recall that if we have a function, it's possible to get two elements which will be mapped to the same element in the codomain. So suppose this is A1, this is A2, and they both get mapped to B. So there is another element here. So definitely this one should go to another element in B. Let's call this B prime. So that is for a function. Now, what we want to happen is for this configuration not to happen. We don't want two distinct elements in the domain to be mapped to the same element in B. If that is the case, we say that a function is injective. It says here that distinct elements of A are mapped to distinct elements of B. So this is saying that if you have A1 and A2, they are distinct from each other, then they should go to different elements. F of A1, F of A2, something like that. You cannot have this one, right? So how do you write that symbolically? It's important that you write the definition of F being injective in symbolic form. This means that for every two elements in the domain such that they are distinct, then they should have different images. So F of A1 must not be the same as F of A2. Now, usually, we don't want, of course, to work with negated statements. So we work with the contrapositive of this statement, this implication here. So this becomes for all A1, A2 in A. What is the contrapositive of this statement? If the images are equal, then the pre-images A1 and A2 must be the same. So this is what we use to show that a function is injective. Injective functions are also called one-to-one. And again, this means that each element in the codomain is the image of at most one. Take note that we have at most one because this is still open to the possibility of having an element in B which does not go to an element in A. Correct? So it's possible to have extra elements in B. So this is how an injective function look like. So therefore, this one, there is a unique element in the domain such that that is the image. So that's like for number 1, it says here that if you get an element in B, it's possible that it has a pre-image, or this case over here, there is no element in A that maps in B. So just like in the case of B prime here. So for example, our set A is this set. We define the function f to be this set of ordered pairs. Take note here that f is one-to-one because each element of B is the image of exactly one element in A. So that is the case for 1, 3, and 4. And for the element 2 in B, there is no element in A that gets mapped to 2. So this is still okay. It's possible to get extra elements in B if a function is one-to-one. But of course, a definition of a function says that there are no extra elements in A. Okay, what about this one? Is this one-to-one? Definitely no, because 2 and 3 gets mapped to the same element 3. How do we now show that a function is injective? So suppose that we have a function from A to B. Recall that our definition of an injective function is that for all A1, A2 in the domain, if their images are equal, remember this definition because this will give you the structure of your proof. Then you must show that the two elements in the domain must be the same. So that's why step 1, we have for all A1, A2, and A. So that's why we start with let A1 and A2 be elements of A. And then here you have this implication. So that's why you are assuming that f of A1 is the same as f of A2. And you need to show this. You need to show that they are the same. So we will use that to show that this function is injective. Of course, the graph of this function is just a linear function, and a linear function is 1-to-1, correct? So to give a formal proof, it's like this. For our step 1, let's call that x1 and x2. There are two elements in the domain, set of real numbers, and then assume, this is our step 2, assume that f of x1, they have the same images. So in other words, 2x1 plus 1, that's f of x1, is equal to 2x2 plus 2. That should be 1. And of course, subtracting 1 from both sides, we get 2x1 equals 2x2, and then dividing both sides by 2, I'm no longer writing it. So there, we have just shown that the pre-images x1 and x2 must be the same. So that is the end of the proof. Now, suppose we define the function f from R to R, set of reals to the set of reals, defined by f of x equals x squared. Which one is injective? Is the function f or the function restricted to 0, infinity? So take note that the graph of the function f is just a parabola, correct? And of course, from your knowledge of algebra, this is not 1-to-1, correct? Because it does not satisfy the horizontal line test. The horizontal line test actually makes us look at one particular value of y. This is one particular value of y. Let's call that y prime. And then, oops, there are two distinct elements in the domain which gets mapped to y prime. Correct? So f is not injective. But how do we show that something is not injective? Not just by looking at the graph. We really have to give a proof that f is not injective. If you look at the definition of f being injective, what is now the definition of f being not injective? So we have f is not injective if and only if our quantifier here is for all, so therefore this becomes there exist two elements in the domain such that these are the same. F of A1 is the same as f of A2, but, so that's and, they are distinct. So this means that all you have to do is to give a counter example. To show that a function is not injective. So for a proof of this, as a counter example, what will be a counter example? Let's say when x1 and x2 are equal to 1 and negative 1, correct? So we can say take can just leave the tick. We can just write, note that f of 1 is equal to f of negative 1. And of course, 1 is not the same as negative 1. So this one statement already proves that f is not injective. What about the restriction of f on the interval 0 to infinity? Recall that the restriction of f on 0 to infinity is just the same function f, except that its domain is now 0 to infinity, and then the codomain is still the set of real numbers. And it takes x, so this is the notation for that. The image of x is still x squared. Is this injective? Take note that if we get the graph of the restriction of f, you just have to remove the one on the negative side. So the graph would be just this one, right? And therefore, this graph is now injective. So let us really prove that this is injective. So for our proof, what do? We get two arbitrary elements in the domain. The nice thing about here is that the domain is now the set of non-negative integers. So we let x1 and x2 be elements of the domain. That one, we're doing step 1, two arbitrary elements in the domain, and then assume that they have the same images. So we can just say such that f of x1 is equal to f of x2. So this means that x1 squared, I'm no longer writing in sentences, you just have to fill that up. Okay, can we say that x1 and x2 are the same? If our x1 and x2 are just real numbers, alright, x1 will be equal to plus or minus x2. If we are working with a set of real numbers, that's the reason why f is not 1-to-1. However, our x1 and x2 are non-negative. So here, you really have to say that since x1 and x2 are non-negative real numbers, then this means that we can conclude that they must be the same. So that is the reason why the restriction of f on the set of non-negative integers is injective. So from our example, we have just seen that injectivity depends on the following: on the domain and the rule used to define the function. Okay, so these two functions f, they have the same rule, but they have different domains. And we found that f is not injective, whereas this one is injective. Here's another example. Here is a piecewise defined function. How do we show that a piecewise function is injective? Whenever you are working with piecewise functions, you would certainly have to have proof by cases. So again, we start with getting two arbitrary elements in the domain. So that means we have two integers. So let n1 and n2 be two integers, and assume that, or you can just say such that, so that means that's another premise. So assume that f of n1 is equal to f of n2. Now, what can we say about these two arbitrary elements? We have to divide them into cases. And what will be the first case? Case 1, n1 and n2 are both greater than or equal to 0. So if that is the case, what is f of n1? That's equal to n1 plus 1, and f of n2 is n2 plus 1, which means that n1 is equal to n2. Okay. I am not writing in sentences again, but in your case, you should always write in sentences. For case 2, For case 2, we assume that they are both negative. If they are both negative, then f of n1 is n1 and f of n2 is equal to n2. So we're done. So the last case is when one of them is positive, or when one of them is greater than or equal to 0 and one of them is less than 0. So you just say, without loss of generality, you should just say n1 and n2 have different signs, or one of them is 0. Okay, so without loss of generality, I should just put my proof here. So this is the continuation of case 3. So without loss of generality, that's the meaning of that one. Assume that n1 is greater than or equal to 0 and n2 is less than 0. Okay, if this is the case, my f of n1 would now become n1 plus 1, and f of n2 would be equal to n2. What is this saying? Take note that n1 is greater than or equal to 0, so therefore this one here is strictly greater than 0, and n2 is negative, so therefore this is less than 0. But your assumption here is that f of n1 is the same as f of n2, but this cannot happen. So in this case, f of n1 is not the same as f of n2. So that means we have a contradiction, because our assumption is that f of n1 equals f of n2, and we got here that f of n1 is not the same as f of n2. So this means, what does it mean if you have a contradiction here? This means that this case cannot happen. Meaning to say, you cannot have two images. You cannot have two elements in the domain. One is positive and one is negative, wherein they will be mapped to the same element. So we're always sure that they will be mapped to different elements, and that is exactly what we want. An alternative way to prove this is to assume that f of n1 equals f of n2, and then you have case 1 and case 2. And then for case 3, you will prove the original statement. What is the original statement? This one. For case 3 here, this one. You need to show that if they are distinct, then the images are not the same.